Hi, so I want to welcome you to Introduction to Economic Analysis class. In this class, we're going to continue what we learned during mathematics, but now our focus is going to be on how to apply everything we learned in mathematics into different economic problems. Of course, sometimes those economic problems are going to be involving from us more knowledge than we already attained, so the new mathematical tools will be introduced as well. But before we move to the subject, let me just remind you that we are still using the same book, so Alpha Chiang, Kevin Wainwright, Fundamental Methods of Mathematical Economics, and tell me a little bit about how your grade is going to be composed. So, your grade has two components. First one, worth 40%, is coursework. And coursework will be associated with the tasks you are supposed to do in the workshops. You have the workshops with Miss Valeria Yersh. She will tell you what you need to do in order to get this part of the grade. Then, at the end of the semester, we will have final exam worth 60% of your total grade, and during the final exam, you will have to solve problems. Give economic interpretations to different solutions about everything that we are going to discuss in this class. Okay, I'm also going to create a Facebook group for this class where I'm going to be sending you some materials that should ease your learning. Because this subject is not as easy as mathematics. Because in this case, it is not sufficient to be able to solve the problem. You need to understand the problem, and you need to be able to give proper interpretation of the outcome that you are going to get. Okay, so at this moment, you already know that we are going to be discussing use of mathematics in economics. The question is, why? Well, economics is a social science, so doesn't matter how good you are and how many equations, variables, models are, or how big the model is, you're never going to be able to include everything that can affect some phenomena. However, sometimes this is not necessary. And as you probably already seen in microeconomics, economics uses models, some simplifications of reality. And the fact is that when we use mathematics in order to express them, we can never get the answer wrong. Why? Well, because construction of every model requires a set of assumptions within which this model is true. So, as long as those assumptions are fulfilled, the model, assuming that it was calculated correctly, is going to be truth as well. So, in this case, we've got first advantage of mathematical approach. Within a given set of assumptions, whatever we're going to get at the end is true for this set of assumptions. And, of course, then what we can do is relax some assumptions. For example, you learned about perfect competition. Sometimes perfect competition is a good assumption of what is happening on the market. But sometimes it is better to use monopolistic competition. Sometimes it's better to use oligopoly models. Sometimes even monopoly. So depending on a particular situation, we can relax some assumptions and see whether something is actually changing in the model, or maybe it stays the same. If it stays the same, it means the model can be made more general. But about it a little bit later. Well, another advantage of mathematical approach is brevity. What do I mean by brevity? Is that you can not only explain everything in a very consistent way, but also in a very short way. Actually, the title of this class, Introduction to the Economic Analysis, comes from the textbook written by Paul Samuelson, that was also by the same name, Introduction to Economic Analysis. And he was the first person who, well, maybe not the first person who used mathematics, of course, in economics, but he written a textbook that was bringing all the economic knowledge into mathematical terms. There were people before him. Actually, we're going to discuss some of these cases even in today's class. But what he said is that what he was learning in the half of a semester of his Introduction to Economics class, he was able to write down on 2 pages of mathematical formulas. And, well, I had the same experience. When I was taking a sociology class, we had a class during which our professor was explaining to us how size of the reward motivates us to do something, and probability of getting this reward also motivates us to do something. And he was talking about it for 2 hours. And by then, even, I was able to write everything he said over these 2 hours in one mathematical equation. Because this is something actually we use in economics, and it's called expected utility, and you're actually going to be learning about it in the future. Okay, so now we know why should we learn about application of mathematics in economics. So now let's go right into subject and what we are going to do in this class. Okay. So we're going to be discussing different economic models. And look, economic model is a simplified analytical framework used to describe economic processes. So economic model is a simplification of reality. Why do we use models? Because reality is so complex, it's really hard to describe it. Even describe it, and especially to make some general conclusions when you have so many forces that actually influence some phenomenon. This is why we use models. Model, in general, not only economic model is a simplification of reality. But the models we're going to be discussing in this class are mathematical models. And we should start by describing what are the ingredients of a mathematical model. And each model, mathematical model that we are going to use, will consist 2 main ingredients. First one are equations. But of course, we cannot have equations without variables. So once we have some variables, we are able to build some equations based on those variables, and then we are actually able to create the full model. We're going to be doing a lot of examples, going step by step, from easier to more and more complex cases, but in this video, we're just gonna learn a little bit about those ingredients, so about equations and variables, and then we're gonna talk a little bit about the equilibrium, but this is for the end. Okay, so let's start with variables. So variables are the elements, the building blocks of every equation and of every economic model. Those are all the phenomena that actually interest us in a specific context. Okay, so first, when we talk about variables, we need to divide them into two separate categories. First one are endogenous variables, and the second one are exogenous variables. Okay, so those are the first two relatively complex names, but I hope you can see that those two names are actually very similar. Like this part and this part is the same in both. Okay, and look, as usually happens in science, when words sound kind of weird, it means it came from Latin. Okay, so what means exo and what means endo? And exo means from outside, it means outside. And endo, inside in this case. So, the main difference between those two set of variables is that the values of these variables are either explained within the model, like in the case of endogenous variables. We can say that in this case, variable is explained within the model. And here, of course, we've got a separate category. So look, if those variables are explained within the model, then exogenous are variables, well, maybe variables, explained variables explained within the model, variables explained outside the model. So look, generally, if we are going to build an economic model, we are going to have different sets of variables. The endogenous variables are the variables that we are actually going to describe with the model, so how they are behaving. However, those exogenous variables, those are the variables that we use to explain their behavior. So we are assuming that their behavior is specified in a given manner. We're not trying to explain why is it so. We're just using them to get the predictions on those. Okay, but this is not the end. But of course, look, this division is the main one, and understanding the difference is key not only to understand how every model in this class works, but basically how the model in any of your economic classes will work. You've already probably seen some version of this distinction in microeconomics class, but of course we will get a little bit deeper into the subject in this class. Okay, and here we will be dividing this group into two additional subgroups. One are going to be parameters, and the other will be constants. And look, here the distinction is straightforward, like from mathematics class. Look, if we have a function, let's just say y equals ax to the power of b minus cx plus d. In this circumstance, you remember what could be called a parameter, what could be called a constant. Look, if we are assuming that this is one of the equations we are using in our model, right? And let's just say that y and x are endogenous variables, because this is just one equation from the model. Then, right away, what can we see? This is a constant, right? So, this is the type of variable that is given exogenously. We are not trying to explain the value of a variable, we are taking it as a given. And in a similar fashion, parameters will be all the variables touching other variables. So you see, this is a coefficient on x, so this is clearly a parameter. This is a coefficient on x, clearly a parameter. But here b, we are taking x to the power of b. For some reason, this is also a parameter. After mathematics class, I don't think this distinction should bring you any trouble. Okay, the key distinction and what you should remember is that simply parameters and constants are the things are given to us exogenously. We are not trying to explain it. Okay, so we've dealt with the first ingredient of a mathematical model. So we need to now move to another one. And another one are equations. Okay, so generally we will be distinguishing between three types of equations. Okay, number one, let me just get some cards. Okay, number one is going to be definitional equation. Okay, so definitional, look, I will not require from you to know all those definitions by heart, but I definitely will require from you knowing what different type of equation is. So please try to understand it very well. So, but let's start with the definition of definitional equation. Okay. Equation, and this is the equation that sets up an identity between two alternate expressions that have exactly the same meaning. Okay, I hope you remember also that we talked about identities in tautologies in case of logics, right? So, definitional equation basically is getting two different expressions and telling us those two expressions are equivalent. So, the best way to understand it is with an example. This is capital letter I, which in microeconomics and for us for a very long time is going to mean profit. So, what is profit? Profit, by definition, you remember three bars, which means that we define profit to be revenues minus costs, right? Those two expressions on each side of these equations are always true, are always the same, because profit is defined as a difference between revenues of a company minus costs. Look, very often we're going to just write it like this, but because actually in economic applications it doesn't make that much difference, but those two are defined to be equal. Well, there's another good example of that you probably haven't started yet in your macroeconomics class, but this is one that you're going to use extensively, and actually we're going to use it extensively in this class as well. And this relationship concerns aggregate expenditures. So those are all the expenditures in the entire economy of some country. How do we define it? Well, those are expenditures of households, which we call consumption. Those are expenditure of companies, which we call investment. Those are expenditures of the government, which we call government spending. Well, later we will also add to it another component called net exports, which is the difference between exports and imports, but I don't want to cloud anything right now and start by too much. This concerns closed economy. This is what we need to add when we can buy and sell goods from abroad. Okay, so now let's go to the second type of equation. And this is behavioral equation. Now, behavioral equation is the equation that specifies the manner in which, you see, even I have problems recalling proper definitions, in which the manner in which variable behaves in response to to exchange or to changes in other variables. Okay, so look, behavioral equation. So we are going to be describing behavior of some variable. And let's again start to explain this with examples. Look, for example, cost. Total cost function depends on fixed cost, right? So how much the company needs to pay even if it does not produce. Let's just say it's some number, 110. And how much company needs to spend when the company actually produces. So let's just say that we've got this as an expression 3q squared. So in this case, we are actually describing behavior of total cost as a function of how much our company is producing. So in this case, we are simply trying to show some specific pattern of a behavior of one variable depending on the behavior of the other variable. Okay, another example, also from microeconomics that you might know very, very well, is quantity demanded. Let's just say that this quantity demanded is, I don't know, 40 minus 3p, where p is price. So what do we have here? Look, we see that when the price is getting bigger, we've got minus over here. This expression, quantity demanded, is getting smaller, right? Makes sense? Well, of course, the law of demand says the higher the price, the lower the quantity demanded, ceteris paribus, of course, other things being equal. So, we've got here described exactly this type of behavior. We see that how much customers want to purchase depends on the price, right? The higher the price, the less they want to purchase. Okay, now finally, we've got a third type, which is actually made of two subcomponents, and those are equilibrium conditions. Okay, so we've got number 3 is conditional equation. And conditional equation is an equation that states a requirement, to be satisfied. Okay, so look, this is the type of equation where we would like our economic model to achieve some specific state. But before this state is achieved, some conditions need to be met. And basically, we get these conditions in conditional equation. Now, what are those conditions? So, what type of state we would like to achieve? First of them is something that you definitely know from microeconomics, but you should know both. Actually, it's an equilibrium condition. And so, what is the equilibrium condition? It describes, this is an equation that describes prerequisites for the attainment of equilibrium. What is equilibrium? I hope you understand from microeconomics, but we will, as I said before, we're gonna actually go back to this notion at the end of this video. Element of an equilibrium. So, you definitely know a lot of equilibrium conditions from microeconomics. Maybe not a lot, but at least a couple. What is the example that you should definitely know is this. Quantity demanded equals to quantity supplied. This is an equilibrium condition, so only if this is satisfied, we will have equilibrium quantity and equilibrium price on the market. Other example, again now, this is going to be from macroeconomics, and I know you haven't done it yet, is a very famous investment equals savings a condition that again we're going to actually go back to it in the future. Okay, and finally, the second type of condition is optimization condition. We've done a lot of optimization in our mathematics class. So you, for example, know that to find a maximum or a minimum, first derivative needs to be equal to 0, right? Okay, so so optimization condition. Describes prerequisites for the attainment and of an optimal value. Okay, so look, as we said, in mathematics, we learned, for example, that to find maximum, the condition is that first derivative is equal to 0, second derivative is negative, right? But this is a mathematical condition, right? We know it by from analyzing the behavior of different functions and noticing that the slope of the function at maximum and at minimum is equal to 0. However, this condition can be translated into economic terms. And as I already showed you in mathematics class and as you've seen in your microeconomics class, the condition for profit maximization is that marginal revenue equals to marginal cost. Right? This is the same condition. So as to say that in order to attain maximum, first derivative of the function must be equal to 0. And look, we know that if we maximize the profit, this is formula for the profit. If I differentiate profit, as we did in case of, as we did in mathematics, we're going to get out of total revenue, we're going to get marginal revenue, and instead of total cost, we're going to get marginal cost. And this should be equal to 0. But look, this condition is basically, well, it's not only basically, it's simply the same as this condition. So here's the one optimization condition that we know, and we actually, using the tools of mathematics, we give it a very, very nice economic ring to it, and economic interpretation. Okay, there are also different optimization conditions which you haven't studied yet, but I'm just going to show you one that we're going to do in the future, and it says that in order for the customer to achieve highest possible utility given budget and prices of goods, marginal rate of substitution must be equal to minus to the negative of relative price of these two goods. Okay, so now we've got all the ingredients, but still there is one thing we haven't discussed as much as we should. Because look, thing that we are going to analyze in economics, and something that actually appears in economics over and over again, doesn't matter which textbook you're going to take, macroeconomics, international economics, there is a term that always appears everywhere, and this term is equilibrium. And sometimes we can actually say that we understand what an equilibrium is, more or less, right? But today, let's give it a proper, nice definition. So, equilibrium is a constellation of selected interrelated variables so adjusted to one another that no inherent tendency to change prevails in the model they constitute. Well, okay, look, this is very nice definition of equilibrium. Actually, equilibrium in an economic model. So this is perfect for us. But let's see what we've got here. Well, we've got some constellation of selected interrelated variables. Let's start with this. Look, what does it mean is that we've got a model in which we've got different variables. And those variables have impact on each other. Some of them are exogenous, so given outside the model, so but some of them are endogenous, so they can they can influence one another. So this is what we've got. We've got like a set of variables that are having some influence on one another. But look, then we move further and we see that so adjusted to one another. So look, out of all the possible configurations of these variables, we choose one or at least some. Sometimes we can have multiple equilibria, but this is something that we're not going to discuss here. So I'm going to stick with one. We're going to move to multiple equilibria in the future. So they are adjusted. It means they are in a very specific proportions to one another. That. Okay, and we get no inherent tendency to change prevails in the model they constitute. So look, basically, once we are, what this last part says, is that once we are actually getting those specific values of the variables, the model like dies out. Not is that in the case that it's useless, but things stop changing. Model stops at a specific point. This point can be, two-dimensional, but it can be three-dimensional, n-dimensional in general, but it stops moving. Basically, we've reached a point at which all the conflicting forces within this model are balancing each other in a specific manner that nothing changes. This is an equilibrium. Okay, but two things to say. Like, first, look, this notion of equilibrium is what we are going to be analyzing thoroughly in this class. Because actually in this class, we're going to do just 3 subjects. One is called static, second is called comparative static, and the third one is called optimization. What do we mean by static? By static, I mean that there is no inherent tendency to change. So we're going to be analyzing, in the first part of this class, we're going to be just seeing examples of different equilibrias. What do I mean by that? So we build a model and we try to see where does it lead us. So what is the equilibrium? In the second part, that we're going to call comparative static, we're going to go one step further. We're going to assume that equilibrium in some model is reached. So we are at some equilibrium, but something changes. The model is thrown out of the equilibrium and it moves to a new equilibrium. And then we are comparing the two equilibriums. So this is what we call comparative static. And then we're going to do optimization, which is the specific type of finding equilibrium, and also moving to another. We can also do comparative static in terms of optimization, but the rules are the logic is basically the same. In case of optimization, we are simply trying to look for the best solution from somebody's perspective, and that's it. Okay, and I think at this moment, this should tell you what is an equilibrium in terms of mathematical economics, mathematical models that we use in economics. You should be able to see where are we going, what are we going to do in this subject. And don't worry, because next semester we're going to be doing dynamics. So what happens when we go from one equilibrium to the other, what happens in the meantime, or whether if a variable is thrown out of the equilibrium, whether it's going back to equilibrium. But first we need to learn this to properly understand the future subjects. But I think one question that should come to your mind is, at this moment, is like, but this concept is extremely, extremely abstract. If economy, if society is made out of so many people, there are so many conflicting interests, there are so many things that happen every second, how is it possible for this complicated system to achieve a state in which all the variables are so adjusted to one another that no inherent tendency to change prevails? Well, that is actually a very good question and a very interesting one. Remember that, of course, in this class and generally in economics we use models. We use models because reality is so complex, it's really hard to understand everything at once. So we just take part of it, very simple parts, we put them together and we see what happens in them. But then, can this equilibrium exist in the real world? Well, I had a lot of different conversations with my colleagues about it, and I can tell you one condition, one couple of things that actually shows us that even in the society, something like equilibrium must be prevalent. One very simple proof is that when you live we are in Poland, right? At this moment, well, some of us, at least. Have you noticed that when you go to the street, we are not all killing each other? Yeah, probably you did. And when you think about it, we have a lot of different reasons to start killing each other. This guy has more money than me. He's got nicer pants or something. I want to take his stuff. He looked at me wrong. Like, there is a million different reasons why people could be going to the streets and fighting each other, taking each other's stuff, beating each other up. We don't do it for some reason. Why we don't do it? Look, in primitive societies, stuff like this was happening all the time. But through the evolution of institutions, so of the framework in which we live, we've came up with some with some solutions that created a society in which we can peacefully live and achieve our goals without being worried that somebody's going to take all the stuff I've worked for the entire day today. So this is this equilibrium I'm talking about. That even though there are so many of these forces, we create a system that works in a specific way. This is not happening on the global scale. Because of course, there's somebody who's stealing from somebody else every day. There's somebody murdering somebody every day. But still, it's not happening on a global scale. Because maybe not all the variables are so adjusted that no inherent tendency to change in this prevails, but it works. However, look, this is not said, this doesn't mean that this equilibrium will prevail forever. A good example of that is what happened after Hurricane Katrina in the United States. What happened after that was that people, facing this tragedy, some of them were just stranded on the top of their houses, couldn't get anywhere. But what happened that there were people there were created groups of people who were raping, murdering, stealing, everything. And look, this is what I'm talking about. Because of this horrific event that was occurring in Katrina, something switched in the people's minds, and they thought that was okay. And they went back to this horrible chaos that definitely has nothing to do with the social equilibrium. So it can happen. So we should not take the equilibrium for granted, whatever we try to imagine. And remember, this has happened in the richest country in the world, right? So it can actually happen everywhere. Okay, so I think this is it for the first video. We've considered a lot of prerequisites, so basically all the necessary concepts that we're going to use in this class. The rest of the class will be very different. It means we will be going, we've got this model, we're solving it, what are the conclusions, what could we add, what could we change in this model. But from this moment on, we're going to be focusing our attention on models in such a way that we can actually learn all three of the subjects that we discussed. So I'm going to actually give you a couple of models as examples, and then we're going to be making them more and more complex, so they actually contain more of the reality within them. And the second thing is we're going to be trying to do different things with those models. We're going to start by establishing equilibrium, then we're going to move to comparative statics. So what happens when we reach the new equilibrium? And finally we're going to move to the subject of optimization. Okay, so thank you for your attention and see you in the next video.